is a multiple of A. And one can easily see that 1 minus 1 are divisors of any integer, and every non-zero integer is a divisor of 0. And when A doesn't divide B, we write this symbol A doesn't divide B. So for example, 5 doesn't divide 13. So this is a very basic starting of number theory. And you have other properties like linear combination of if A divides B and A divides C, then A divides the linear combination of B and C, and is transitive. A divides B, B divides C, then A divides C. And one Archimedean property, sort of Archimedean property, is that if B is positive and A divides B, then A is less than or equal to B. And of course, if A divides B, then minus A plus minus A divides plus minus B. So these are some very basic facts. So of course, all of you are familiar with primes, and Abhishek gave a nice introduction to primes. I will go a little bit faster on this. So I just want to tell you that, of course, all of you know what's a composite number. Now, I want you to think why we don't take n is prime or a composite. So when we take a number to be prime, we take p to be bigger than 1. And so when we take a number to be composite, we take that number to be bigger than 1. So we don't take 1 to be neither a prime nor a composite. So why do we do that? Actually, it comes from this fundamental theorem of arithmetic. So which all of you know, every integer can be a positive integer can be written uniquely as product of primes, product of prime powers. So of course, so 100, as you can see, you can write it as 2 square into 5 square. Now the thing is that if 1 is a prime, then it's going to violate the fundamental theorem of arithmetic. So you can write, say, for example, 10 as 2 into 5, then 1 into 2 into 5, 1 square into 2 into 5, 1 cube into 2 into 5. So you can write any power of 1. So then that will violate actually the fundamental theorem of arithmetic. That's why we don't take 1 to be either a prime or a composite. And one takeaway from fundamental theorem of arithmetic is that every integer bigger than 1 has a prime divisor. And that is the basis of infinitude of primes, which is the Euclid's theorem. So since this was, this is a proof by contradiction, which all of you are familiar. So I don't have to give you, but basically I'll just repeat a little bit in the sense that here, this is the first proof by contradiction. Is one of the first proof in mathematics, and is one of the most beautiful proofs in mathematics. So if there are only finitely many primes, you multiply them and add 1. That has a prime divisor, and none of these primes P1, P2, PR divides it. So it has a prime divisor outside P1, P2, PR. So that tells that set of primes has to be infinite. So this is one of the most basic and most fundamental, one of the first nice proofs in mathematics. So we're going to write a sequence of primes by P1 equal to 2, P2 equal to 3, P3 equal to 5, and so on. So Pn means nth prime. Of course. So Euclid's theorem tells you that there are infinitely many primes, but then can you find large primes? So that's still a big challenge for us. We're not technologically that advanced to find very big primes. I'll tell you a little bit more about it in course of time. And right now, the largest known prime is the 24.86 million digit prime, which is a prime of the form of something called Mersenne prime. So this number 825899933 is also a prime. So it's 2 power p minus 1. So this is a Mersenne prime. So now I would like to talk a little bit about this GCD and LCM, which all of you know, but I'll just go a bit faster here. So GCD means the greatest common divisor, which is the largest positive common divisor of A and B. And it's an easy exercise to see that the GCD of two numbers can be written as linear combination of AX, linear combination as X plus BY for some X and Y. And when A and B are relatively prime or co-prime, then we say, so that happens if and B. So when GCD is 1, we call them relatively prime or co-prime. And similarly, the lowest common multiple or LCM is the least positive integer which is divisible by both A and B. And it's an easy exercise to show that if you know the prime factorization of A and B, then you can write GCD and LCM very easily. So you take the GCD to be the, you take primes common to both of them, and you take the smaller of the powers of that primes dividing A and B. So that becomes the GCD, and the LCM means the larger of the powers of primes dividing them. And one can easily see that LCM and GCD is actually equal to the product of these two numbers. And these are some basic properties. So yeah, so basically GCD of N and M is same as GCD of a linear combination of NM and M, and so on. And of course, I mentioned before, the GCD of two numbers, you can write it as a linear combination of NX plus MY. Yeah, for example, GCD of 3 and 5 is 1. 1, you can write it as 3 into 2 plus 5 into minus 1. So this is quite important, which will, for many number theoretic applications, also used in many of these cryptography related applications. Now I want to tell you about the division algorithm, which all of you, of course, are familiar. So division algorithm means, given a positive integer A and any integer B, there exists unique integer Q and R, such that you can write B as AQ plus R, with R lying, R is a number which is either 0 or strictly less than A. And when B is equal to 0, you can take Q and R to be 0. So 0, you can write it as A into 0 plus 0. And it's quite clear that when A divides B, then GCD is 0. No, the remainder is 0 and vice versa. So remainder is 0 if and only if A divides B. So number Q is the quotient, R is the remainder. And both quotient and remainder are unique. So why I'm bringing the division algorithm is that, so I showed in the previous slide, if you want to find the GCD of two numbers, if you know the factorization, the GCD can be computed very easily. But if you don't know if the numbers are large, it's not easy to factor. So in that case, can you find a easier way to find the GCD of two numbers? So here we need the division algorithm. And one takeaway from division algorithm is that in a set of integers, you can divide the set of integers into some equivalence classes. So for every positive integer M, every integer will be either of the form Km or Km plus 1 or Km plus 2 or Km plus M minus 1. So now I want to talk about this equivalence. So finding the GCD is difficult. I mean, if you are to use the factorization, finding is very difficult. But without factoring the numbers, there's a way to find the GCD of two numbers. That's called extended Euclidean algorithm. So I will explain a bit and give you some simplifications. So it relies on the fact that GCD of two numbers is same as GCD of two numbers A and B is same as GCD of A and B minus AR, and also same as A minus GCD of A minus BR and B. So for take any R, then GCD of A and B is same as GCD of A and B minus AR. So in other words, GCD of A and B is same as the GCD of A and remainder of B when divided by A, or GCD of B and remainder when A is divided by B. So that's the main thing which is coming from this lemma. So to find the GCD of two numbers, you can just have to look at the remainder of one of them. Take the GCD of the smaller number with the remainder of the bigger number when that is divided by the smaller number. So I just want to show you the GCD algorithm, which is Euclid's algorithm. We need to find the GCD of two numbers. So I'm going to show you with an example. So of course, if B is 0, then GCD is A. Otherwise, you take the GCD of A and remainder when B is divided by A. So for example, you take A to be 260, B is 412. Now remainder of 412 when divided by 260 is 152. So GCD of 412 and 260 is same as GCD of 260 and 152. Now GCD of them is same as GCD of one smaller is 152, and the remainder when 260 is divided by 152 is 108. So then you need to take the GCD of these two numbers 152, 108. Then again you play the interchange the role of 152 and 108. So then it's a GCD of 108 and remainder when 152 is divided by 108, that is 44. And again 44 is the smaller number, then remainder is 20. So GCD becomes, sorry, GCD of 44 and 20. And again 4 is the remainder when 20 divides 44. So then it becomes the GCD of 20 and 4. Finally, you have this remainder is 0. So GCD of 4 and 0. But 1 0 is there, you know that GCD is 4. So the GCD of these two numbers is 4. This is how the Euclid's GCD algorithm works. It's just a simple idea that you can write any number B as A times Q plus R. Of course, in practice, one can make it much simpler and make it more effective. So there we use so-called binary Euclid's algorithm. Because in computers, they only understand binary numbers, and you have to write every number in the binary form. So what they do is they use an efficient algorithm using the following idea. So what you do is that you write A as some power of 2 times an odd number. So you see, if you want to know the power of 2 dividing any number A, it's very easy in computer. You just put that number. When it writes in binary, number of zeros at the end, that's the power of 2 dividing A. So for example, when you plug A, number of zeros at the end in the binary expression, that is the R. So you take out the powers of 2 and write the remaining number, remaining part, that is A1. A1 is odd. Similarly, B is 2 times S times B1, and B1 is odd. So you have taken out powers of 2, and you are now left with A1, B1, which are both odd. Then one can easily see that GCD of A and B is GCD of 2 power T, where T is the minimum of R and S, times the GCD of A1 and B1. So I've taken out the powers 2, then I have to find the GCD of A1 and B1. So now I'm going to again use the fact that given n, let n not be the odd part of n. So odd part of n means you take out the powers of 2, remaining part. So then GCD of A1, B1, these are both odd. That is same as GCD of A1 and B1 minus A1, right? Because from the previous lemma, we can see that GCD of A1, B1 is same as A1 and B1 minus A1. So which you can write it as GCD of A1, and because since GCD is odd, so you can take out the odd part of even part of B1 minus A1. So you just consider A1, GCD of A1 and the odd part of B1 minus A1. So and we continue like this. So this is called binary Euclid's algorithm. So let me give you an example. Yeah, so let me give you the algorithm. So basically, you start with two numbers A and B. If both are even, then you take GCD of A by 2, B by 2, and one of them is even, other is odd, then A by 2B. So basically, this is just the binary Euclidean algorithm I was showing you. So let's look at this example or earlier example in this form. So we have to find the GCD of 412 and 260. So B is 2 square into 103. So 103 is the odd part of 412. And 65 is the odd part of A. So GCD is 4 into GCD of 103 and 65. And where to show that this GCD is 1, 103 and 65 is 1. So finally the GCD is 4. Now the GCD of 103 and 65 is the GCD of 65, and you take out the so odd part of 103 minus 65. So 103 minus 65 is 38. So yeah, so there's a typo here. It should be 19 anyway. So then it becomes a GCD of 65 and 19, and again 19 and 65. Yeah, so now assume that is 17, but it should have been 19. So 19 and 17 and 65 minus 17, the odd part is 3. So you need to take the GCD of 17 and 3. Then you take out 17 minus 3, GCD is odd part is 7, because 14 you take out power of 2, so only 7 remains. So GCD of 3 and 7, and that is same as 3 and 1, because 7 minus 3 is 6, so odd part is 3. So yeah, so 7 minus 3 is 4, the odd part is 1. So GCD of 1 and 3, then it just becomes 1. So this is how you get binary Euclid's algorithm. So one of the so take away from this Euclid algorithm is that you can write the GCD as a linear combination of the previous two numbers. So for example, from this GCD of 412 as 260 to 152, you can write number 4 as a linear combination of 260 and 150, 412 as 412 into 12 minus 260 into 9. So just that the way you write this Euclid's algorithm, number 4 you write it as 44 minus 20 into 2, then 20 you write 108 minus 44, then it's a linear combination of 44 and 108. Then 108 again you use 260 and 152 and so on. So this is how we have this GCD can be written as linear combination of two numbers. So yeah, any questions so far? Okay, so so then I'll just continue. Let me just. Oh, sorry. I think there's some issues. Yeah. Let me just see. Okay. All right. So now I want to talk a little bit about the modular symbol. So modular symbol is nothing but so of course Abhishek also talk about the clock is modulo 12. So every number every hour can be written as modulo 12. So that way we say that A is congruent to B modulo 12 modulo M if M divides A minus B, and write A is congruent to B mod M. And so it is some nice simple elementary properties, like if A is congruent to B, then B is congruent to A, and AX is congruent to BX mod M, or A is congruent to B, C is congruent to D, then X plus CY is congruent to BX plus DY. Not only that, you can take powers. A power N is congruent to B power N modulo N. So these are basic properties which are quite easy to see from modulo symbol. And in fact, A modulo M is, you can think about it, is a remainder of A when divided by M. So one thing which is coming, so now we can give a group structure on this modular arithmetic. So given M, you can take GM to be the numbers which are all remainders when divided by M. So these are 1, 2, 0, 1, 2 up to M minus 1. And you can define an operation, additive modulo M operation as I plus J modulo M is I plus M, this symbol I plus M G is I plus J modulo M, and multiplication is I into J is I J modulo M. Then under this operation, GM, this set forms a ring, and one can see that every integer, every positive integer, so if you take the remainder when A is divided by M, it belongs to GM. So we call A to be invertible modulo M if A and M are co-prime, and if A into M modulo A into B modulo M is 1. So A is invertible if there is some B such that A into B modulo M is 1, and we call B to be the inverse of A mod M. For example, if you take M equal to 7, then 3 into 5 is 1 mod 7. So 5 inverse is 3. Similarly, 3 inverse is 5. Now the question is that given A, how will you find the inverse of A modulo M? So why the inverse is coming? Actually, if you use the RSA algorithm, then you need to take this inverse modulo M for certain M. So we need to know, we need to have a nice algorithm, practical algorithm to find the inverse modulo M. So one of the way to find the inverse of modulo inverse is this: you use the GCD algorithm. So if since A and M is 1, because GCD is 1, so you have x and y such that x plus my is 1. So in that way, so that means x is congruent to 1 mod M. So A inverse is nothing but the x modulo M. So this is how we find our inverse. Now if you take the set of all numbers A in GM such that A inverse exists, then it forms a group. And number of elements in this group is called the Euler phi function or Euler Taussian function, and it's multiplicative. And for a given prime P, you know that every number from 1 to P minus 1 is co-prime to P. So this GM is nothing but set of all integers between 1 to M, which is co-prime to M. So when M is P, number of such elements is P minus 1. So phi of P is P minus 1. And for any M, one can easily show that phi of M is M times product of 1 minus 1 over P, where P runs over prime divisors of M. So in particular, when M is equal to PQ, which are numbers of RS, which are so-called RSA numbers, then phi of M is nothing but P minus 1 into Q minus 1. So this information about P minus 1 into Q minus 1, this is actually essential for cryptographic algorithm, particularly in RSA algorithm. So now let me give you the list of inverse elements in G11. So inverse of 1 is 1 itself, and inverse of 10 is 10 itself. Inverse of 2 is 6, and inverse of 3 is 4. So 2 is 6, 6 and 2. Now 3 and 4 is 12, so inverse of 3 is 4, 4 is 3. Similarly, 5 and inverse of 5 is 9, and so on. So its number is not that difficult, it's small. 11 is very small, so it's easy to compute here. Now, one important property which is given by the modular arithmetics, the Euler's theorem and Fermat's little theorem. So Euler's theorem tells you that since we saw that GM star is a group, so by the property of the group, so A power phi M mod M is 1 mod M. So basically, given any A, you look at the A modulo M, then number of elements is phi M, so A power phi M has to be 1 mod M. Or in particular, what we say, A power phi M is congruent to 1 mod M whenever A and M is 1. This is called the Euler's theorem. And when M is P, where P is a prime and P doesn't divide A, then phi of M is phi of P is P minus 1. So A power P minus 1 is 1 mod P. This is called Fermat's little theorem. So in fact, from here, so we can get the inverse of a number. So from here, we can write that A inverse of is A power phi M minus 1 modulo M. But then, like given M, computing phi M is not that easy. So so we usually use the earlier way to like GCD algorithm to compute the inverse of mod M. So, and by the way, this Euler's algorithm, this is the basis of RSA algorithm, which is one of the most widely known algorithms. So now the question is that many times we need to take powers of numbers modulo M. So how do you take powers? So we don't want to keep multiplying, but then we have to make an efficient algorithm to take the powers. So there's a notion of square and multiply algorithm, which I just want to show you. So to compute A power n modulo M, so to compute A power n modulo M, we write n in binary notation as nl, nl minus 1, and so on. Then you compute the square. So A square mod M, then A2 is A square of square. So that is A2 whole square mod M extra. So you can do it by successive squaring. Then A power n is nothing but you take the parts a1, a2, etc., where these NLs are non-zero. So basically, what in this example, if n has this form 100100011 in binary notation, then a power n is a power 2 power 7. So 0, 1, 2, 3, 4, 5, 6, 7. So a to the power 2 power 7, then a to the power 2 power 4, and a square and a. So, and you just take these numbers by using successive squaring. So this is called square and multiply algorithm. So this is the modular exponentiation. So if you want to compute the powers a power j mod m, you take a m j times. So basically, uh, by using square and multiply algorithm, you take a power j mod m, and for any number a here and ij integers, you take a power I mod m into a power j mod m as a power I plus j modulo m. And similarly, a power I modulo m power j is a power ij mod m. So this is the modular exponentiation. So this is how actually which is being used in practice in the computers for efficient modular exponentiation. So this is the algorithm. Those who are familiar with the algorithm, so this is called a fast exponentiation algorithm. So given integers a, p, and m, it computes a power p mod m. So basically, you take successive squaring and uh, then put it together. So this is how you do it. All right. So okay, so this is just an example. I'll just go further. Now I want to also talk to you about Chinese remainder theorem. So this is also essential. So one thing is that the binary Euclid's algorithm or GCD algorithm can be used to solve a system of equation, can solve a linear differential equation, but we require this when you are given a system of equation, then we require something called Chinese remainder theorem. So let me state it for you here. Given relatively prime positive integer m and n and any integers a and b, if you look at the solution of the simultaneous equation, x is congruent to a mod m and x is congruent to b mod n, then it has a solution x is congruent to c modulo mn, with c lying between 0 and mn. So basically, whenever m and n are co-prime, then this system of equation has always a unique solution given by some c which lies between 0 and mn. And in fact, you can find c explicitly. So so take n1 to be such that n into n1 is 1 mod m. So basically, n1 is the inverse of n modulo m, and m1 is the inverse of m modulo n. Then c is congruent to a into n n1 plus b into m m1. So this is the Chinese remainder theorem. And this is also, it has a lot of applications in number theory and other areas of mathematics, and of course in cryptography. So of course, Abhishek Adhikari talked about quadratic residues, so I'll skip this part. So basically, quadratic residues and reciprocity layers tells you how to find whether a number is a square modulo m or not. So I'll go here a little bit faster. Okay, so now I would like to take a short break. Not break, but I just want to ask if you have any questions here. Can someone tell me, yeah, if you have any questions so far? Because now I'm going to talk about primality testing algorithm. So I'll talk about facts about primes and about the algorithms. So, okay. Okay, all right. So then let me. Okay, so Yes, let me continue. So, sorry. Okay, so here, yes. Now I want to talk about facts about primes and probability testing algorithm. So let's come to the number. So in cryptography, we require very big primes. So is it okay? So given a number, is it easy to check that number is a prime? So let's start with some example. So if you are given 101, of course, then you can easily check that this is prime, because you can either you can use a sieve of Eratosthenes, or every number has a prime divisor, so you can check 101 easily. If I give you 65537, still, I mean, this number is a little bit bigger, but still manageable. Now I give you 7732917. So of course numbers are getting bigger, but still it's doable. So it's not a not a big number. Now once okay, so if I give you this number, so this number is actually a prime. If I give you 2 power 77232917 minus 1, then it gets quite difficult. But then if I give you the last number, what can you say whether the last number is a prime or not? So if I give you 914, then it may look that it's quite difficult, but it's very easy, because the number here 914623587, this is divisible by 3. It's a multiple of 3. So this is divisible by 2 cube minus 1. So though this number looks very large, of course it's a large, but this actually is quite easy to see that this number is a composite, because this is divisible by 7. Whereas when if the power is prime p, the life is more difficult. So these are so-called Mersenne primes. So now I just want to give you the list of top 10 largest non-primes. So right now, as of today, these are the top 10 largest non-primes. And largest non-prime is 2 power 8258933, which is around 24.86 million digits, which was discovered in the year 2018. And so first at largest primes, so 9 out of top 10 largest primes are Mersenne primes of the form 2 power p minus 1. So now I will tell you about, of course, all of you know, probably all of you also see Kaun Banega Crorepati. Now I'll give you a way to earn some crores. So there's a organization called Electronic Frontier Foundation. They offer prizes for finding large primes. In fact, in August 2008, it offered a prize of $1 lakh. That time, of course, in Indian currency, it was around 45 lakhs. There's something called GIMPS, and University of California at Los Angeles, the mathematics department, for discovering the 13 million digit prime number. Basically, they discovered the first prime number which is more than 1 million digits. So actually you can Google Electronic Frontier Foundation, and still you can see more details there. So now right now the largest known prime is around 24.8 million digits. So if you can find a prime with 100 million digits, then you'll get $1,50,000. And if you can find a prime with 1 billion digits, you'll get $2,50,000, which is of course more than 1 crore. And also there's something called RSA Factoring Challenge. It offers prizes for finding factoring large numbers. So if there's some time, I'll talk about it a bit. So now I come to the number which I started with. So given a number n, is it easy to check that n is a prime? So this was the number I gave in the beginning. All the numbers, all the terms here except 3 are odd, even. So 3 is the odd person out. Basically, it's the odd number out. So sort of. So it turns out that this is a prime, and it has 20,562 digits. So number of digits is 20,562 decimal digits. Basically, it was a sort of challenge for checking whether number is a prime or not, and it was checked using so-called fast elliptic curve primality proving method. So ECPP method. So there they work on several networks of workstations, and basically it involves a lot of steps. So it involves this square root step, Cornesia step, PRP test, computing Hilbert discriminant, and so on. So it started on 32-bit machines in September, October 2005, and finished in 964-bit by processors in February, June 2006. So almost 9 months. And of course, there are different phases that took a lot of days. So all these days are with respect to the computer timing. So with respect to AMD Opteron 250 at 2.39 gigahertz. So these are with respect to computer so time. Basically, if you work in your laptop or PC, it will take a lot. I mean, like the first phase will take 1900 days, second phase will take 319 days, and so on. But there, of course, they used different arguments and they did it together. So it took less than a year. So even this 20,000 digit number to show that it's a prime, it was not that easy. Now, so now imagine if you have to find a prime with 100 million digits or 1 billion digits, then it's going to be quite difficult. Nevertheless, there are algorithms to show that, and to check whether number is a prime or not. So one thing which was talked in the morning so is that the first algorithm to check whether number is a prime is the sieve of Eratosthenes, which is actually based on the fact that if n is not a prime, then it's divisible by prime less than or equal to root n. So either n is a prime or it's divisible by prime less than root n. And but when n is small, this is okay. But when n is large, this is going to be very extremely difficult. Like suppose n is 100 million digits, then it's going to be quite difficult because you need to keep checking by every prime less than square root of 100 million digits. So it's going to be not that easy. Right now, the fastest known algorithm is so-called Rabin-Miller primality testing algorithm, but it's fastest. But then it's a probabilistic algorithm, and it's not deterministic. And there's this elliptic curve primality proving, which I mentioned before, is deterministic, but it's not polynomial time. And Agrawal-Kyle Saxena algorithm, which is invented by or three Indian mathematician Agrawal, Kyle, and Saxena. So this is the only non-polynomial time algorithm, but then it's of course it's good in theory but not good for practical purposes. So of course all of you are familiar, but I just want to tell you that there are different kinds of algorithms. So you have an algorithm of polynomial time complexity. If the running time is bounded by, it's an order of log n power k, where log n is the length of the input n. So you put the input, so log n means when it converts to binary, length is log n and k is some constant. It's a polynomial in log power n, then it's called polynomial time complexity. And it's exponential time complexity if running time is bounded by order of n power epsilon, or for some epsilon less than 1. And there's polynomials in between. There's something called super polynomial time complexity if its running time is log n power c log n. And there's something called sub-exponential time complexity if it lies between, it's neither not polynomial, not it's not as efficient as polynomial time, but it's neither also exponential time, it's somewhere in between. So it's of the form x pop c log n power alpha log n power 1 over alpha. So basically when alpha is 1, then is exponential. When alpha is 0, then is polynomial. So basically for any alpha in between 0 and 1, it's something called sub-exponential. So you can like say the relationships. So polynomial time algorithms are contained inside superpolynomial time, and which are contained inside sub-exponential, and which are inside sub-exponential. So these are something about the algorithm which one can know. So there's this also in the morning, Abhishek talked about it. So there's randomized polynomial algorithms or zero error probabilistic polynomial GPP algorithms or non-deterministic polynomial NP. So what is the what is deterministic? Deterministic means you get for sure that something is correct. Probabilistic means with some probability there may be some error. So this is what makes difference between deterministic and probabilistic algorithms. So now, of course, all of you sip up Eratosthenes. I'll go with first. Now I want to talk about some other algorithms. Now let's come to primitive roots. So let me define for you what's a primitive root. A number G root modulo n. So basically, G is a primitive root for n if every number which is co-prime to n can be written as some power of G modulo n. So basically, G so the G generates the multiplicative group modulo n. So G is a generator of the cyclic group of order phi n, and if n is a prime, then G power n minus 1 is 1, and G power n minus 1 by p is not equal to 1 for any prime p dividing n minus 1. So primitive roots tells you that so G power n minus 1 has to be 1, and G power n minus 1 by p should not be 1 for any prime divisor of n minus 1. So in practice, it's not that easy to find primitive roots. It's a difficult problem also to find primitive roots, but when n has certain form, it may be easy to find primitive roots. So now I'm to talk about this, the converse of Fermat's little theorem due to Lucas. So this is so-called Lucas primality testing algorithm. So a positive integer n is a prime if and only if you can find an element A such whose order of A modulo n is n power n minus 1. That is, A power n minus 1 is congruent to 1 mod n, and A power n minus 1 by p is not congruent to 1 mod on n for every prime divisor of n minus 1. So basically, the Fermat's little theorem tells you that given any A power n minus 1 has to be congruent to 1 mod n. But then Lucas theorem, what it tells you is that n is a prime if not only that this happens, but for every prime divisor p of n minus 1, A power n minus 1 by p should not be 1 mod n. This is the Lucas primality testing algorithm. So let's look at an example. So let's try to show that number n, which is 2011 is a prime. So write 2011 minus 1, you factor it, so it's 235 into 67. So somehow we are able to find a primitive root 3. So 3 is the primitive root of 2011, since 3 power 2011 is order of 3 modulo 2011 is 2010. Now, so 3 power 2010 is 2011, that we can see, and 2011 minus 1 by 2. So 3 power n minus 1 by 2 is minus 1, which is not 1 mod 2011. 3 to the power 2011 minus 1 over 3. This is also not 1 mod 2011. So basically, for every divisor, prime divisor 2, 3, 5, or 67, 3 to the power 2011 minus 1 by any of this prime is not congruent to 1 mod 2011. Hence, by the previous theorem, 2011 is a prime. So this is called n minus 1 primality test. So this is based on the primitive roots. But then, of course, this works well when n-1 has small prime divisors. So if n-1 doesn't have small prime divisors, and then it's more complicated, because first of all, you need to find a primitive root, and secondly, you have to factor these numbers. Now, here I want to make a remark. Since modular exponentiation is quite fast, I mean, once you know that n-1 has a small prime factor, it's nice, but when n-1 is composed of big prime factors, it's not a good algorithm. Now I want to talk about this Fermat test. So that was n-1 test due to Lucas. So this is the Fermat test. So what does Fermat tells you is that it gives something called pseudo prime. So let me define what's a pseudo prime. Given an integer n and a given positive integer n and a number a which is co-prime to n, we say n is a pseudo prime or a Fermat pseudo prime to the base a if a power n-1 is mod n. Remember that Fermat's little theorem tells you that if n is a prime, then a power n-1 is congruent to 1 mod n. But now I don't know if n is a prime or not, but if there's some a such that a power n-1 is congruent to 1 mod n, then we say that a is a pseudo prime or Fermat pseudo prime to the base a. For example, the number 17343, which is 3 squared into 41 into 47, is not a prime, of course, since it's not a prime. But then a number a 163 satisfies a power 163 to the power n-1 is congruent to 1 modulo n. So number n is a pseudo prime or a Fermat pseudo prime to the base a. So the Fermat test runs like the following. So you choose some number t. So for a different number of, you take t numbers at random. So choose some number a, t numbers at random, you test if a power n-1 is 1 mod n. So this is the first step. First check if a power n-1 is 1 mod n. If a power n-1 is not congruent to 1 mod n, then n is composite. So then nothing to so then Fermat test tells you that if you have some t numbers, which is sufficiently large that this a power n-1 is congruent to 1 mod n for each of the number a, then you deduce that n is a prime. Of course, this is a probabilistic algorithm. So the probability of a composite n declared as a prime is 1 over 2 power t. So when t is large, or choose t appropriately, then the error becomes low. So you can get that, basically you can show that n is a prime with very low probability. So that's why it's a probabilistic algorithm. So what it tells you that if something is composite, it will instantly give that it's composite. Yeah, so no, one thing is if, okay, so even if n is composite, sometimes it will say that n is prime with some error of, probability of error is 1 over 2 power t. So this is the Fermat test. Then there's this Carmichael number. So let me just tell you about Carmichael numbers. A prime number n is called as, recall the definition of pseudo prime. Pseudo prime means there's some a such that a power n-1 is congruent to 1 mod n. So if n is a prime, then it's a pseudo prime to every base co-prime to n. And there are numbers which are not primes, and they're pseudo prime to every base co-prime to n. Such numbers are called Carmichael numbers. So the smallest known Carmichael number is 561, which is 3 into 11 to 17. So this is not a prime, definitely, but then, yeah, so it's pseudo prime to every number a co-prime to 561. So so here's the characterization. A positive integer is a Carmichael number if and only if n is square free. Square free means it's not divisible by square of any number, and p minus 1 divides n minus 1 for every prime divisor p of n. So here 3 minus 1 divides 560, then 11 minus 1, that is 10, divides 560, 16 divides 560. So this is the a Carmichael number. Okay, there's some open problem. So set of Carmichael number is finite and it has certain properties is there. Which is still not known. So every Carmichael number is odd with at least 3 distinct prime factors. This is what is known from number theoretic idea. It's not that easy. So because of this existence of Carmichael numbers, we have a bad news if you want to use Fermat test. So there are infinitely many Carmichael numbers. So Fermat test may give, may say that many of these, like if you are given Carmichael number, Fermat test will tell you that it's a prime, but in practice, these are not prime. So it's not that a good algorithm in that way. So now I will, I won't talk about Euler's pseudo prime because Solope-Strassen test was already discussed before. So let me now talk to you about the fastest and most widely used algorithm called Miller-Rabin primality testing algorithm. So let me start with some ideas on how this algorithm works. So it's easy to see that if n is a prime, then square roots of 1 modulo n are plus or minus 1 mod n. So when n is a prime, there are only 2 square roots of 1, either 1 mod n or minus 1 mod n. And for a number n which is not a prime and which is odd, so one can always find another trivial square root of 1 modulo n. For example, for n equal to 15, the number 4 and 11. So these are square roots of 1. 4 square is 1 mod 15, or 11 square is 1 mod 15. So when n is not a prime, you have non-trivial square roots of 1 modulo n. And one can actually show that any Carmichael number has at least 6 non-trivial square roots mod 1. So in Miller-Rabin primary testing algorithm, the main idea or basic idea what we use is that, so we also first check that if a power n minus 1 is 1 modulo n, if it happens, then if a power n minus 1 is 1 modulo n, then it has to have a non-trivial square root modulo n. If n is not a prime, then it's going to have a non-trivial square root of 1. So that is the idea of what used in Miller-Rabin primality testing algorithm. So I'll give you more details here. So let me explain it a little bit more here. So we start with a composite number, odd composite number n, and suppose that a power n minus 1 is 1 modulo n. Now we are going to write n minus 1 as 2 power s m with m odd. So by using this square and multiply algorithm, you compute bj, which is a power 2 power j m for every j which lies 0, 1, 2 up to s. Clearly, a power n minus 1 is congruent to 1 mod m. 1 mod n means b power s is 1. So, and if b naught is 1, definitely bj is 1 for every j. And if b naught is not equal to 1, there exists some unique j such that bj is not 1 and bj plus 1 is 1. And if bj is not equal to minus 1, then it's a non-trivial square root of 1, and hence n is composite. So basically, if you start with n, if you can look at a sequence of b naught, b1 up to bs, if you can find a bj which is not equal to minus 1, then it has to be composite. So that's the Miller-Rabin primality testing algorithm. So yeah, so let me write down this. Let me give you the definition. So N odd composite integer is called a strong pseudo prime or Miller-Rabin pseudo prime to the base A co-prime to N. If B naught is A, so remember that B naught, B1 are the powers of this. So N minus 1, you write it as 2 power Sm. Then Bj is A power 2Jm for every J between 0 to S. So odd composite number is called a strong pseudo prime or a Miller-Rabin pseudo prime if either B naught is 1 or Bj is minus 1 for some J between 0 to S minus 1. And a strong pseudo prime, yeah, so anyway, we're not going to go it. So yeah, so let's look at this example. N equal to 891. You can write it as 3 power 4 into 11, and this is actually a strong pseudo prime to the base 10. I mean, to 10 bases. So for A equal to 182, 164, 10 bases, N is a strong pseudo prime. So basically at 90 minus 1 you factor and you form this B naught B1. So either B naught is 1 or there will be some J such that Bj is minus 1. Similarly, 2891 is a strong pseudo prime to bases 1 and 2, 2890. And N equal to 561 is it has 3 bases, 10, 80, and 322. 4 is N is strong Euler and Fermat pseudo prime. So there are so-called strong pseudo prime numbers exist. So now let me write the Miller-Rabin primary testing algorithm in this following lemma. Let P be an odd prime, and you write P minus 1 as 2 power km with M odd, and take a number A lying between 1 and P. Then either A power M is actually equal to 1 mod P, or one of the number A power M, A power 2M, A power 2 square M is congruent to minus 1 mod P. So given a prime P and given any number A, either A power M has to be 1 mod P, or one of this M number, A power M, A power 2M, A power 2 square M, and so on, or power 2 power K minus 1 M. These are all, one of these has to be congruent to minus 1 mod P. So this is what is being used in Miller-Rabin primary testing algorithm. So let's write down this algorithm. Fix the number T of iterations. You are going to write N minus 1 as 2 power S times M with M odd. For a number I from 1 to T, you choose a random integer A and compute B naught, which is A power M modulo N. If B naught is equal to 1, then you keep computing until you get 1. Bj plus 1 is 1. So if we have Bj plus 1 is 1, if Bj plus 1 is not equal to minus 1, then N is composite. It's clearly N is going to be composite. And if B of S minus 1 is minus 1 modulo M, then N is composite. So none of this happens, then N is a prime. So Rabin Miller is going to say that N is a prime in either case, if these two conditions are not satisfied. So here the probability of a composite N to be declared as a prime is not more than 1 over 4 power 10. Actually, it follows from the fact that the fraction of bases in Zn for which N is a strong pseudo prime is at most 1 over 4. So this is more theoretical. So because of this, so the probability that a composite number N is declared as a prime is not more than 1 over 4 power T. So by choosing T appropriately, we can reduce the error of probability to low value. And one good thing about this Miller-Rabin test is that the running time is log n cubed. So it's a polynomial time algorithm. Only the bad part is that it's not deterministic. It can declare some composite number to be prime. Now, if you use the so-called extended Riemann hypothesis, so I don't have time to talk about extended Riemann hypothesis. Under that extended Riemann hypothesis, actually Miller's algorithm is correct. Actually, it's a deterministic polynomial time in that case. So Yeah, so one so see that if n is m power k for some k or n even number bigger than 2, then one can easily say so that it's composite. And for every other, you take number a lying between 1 and 4 times log square n. Then if one of the numbers in the sequence, either all of them are 1 or it has a -1, then you classify n as a prime, otherwise it's composite. Because of extended Riemann hypothesis, once so if it satisfies, then yeah, yeah. So there's a notion of primitive root. So when a lies between here, there's a primitive root. Because of that, actually n becomes a prime. So without Riemann unconditionally, you cannot say that it's a polynomial time, but under extended Riemann hypothesis, it's a deterministic polynomial time. So yeah, so there's other modification, like instead of doing this test, so you can have some randomized algorithm, and instead of O per log n cubes, you can have a running time of O log n arithmetic operation. This is actually what is used in practice. So instead of trying for all a in some range, you select some number randomly between 2 and 4 times log square n. Now, finally, I want to talk about the Agrawal-Kyle-Saxena algorithm. So this is the only polynomial time deterministic algorithm, and it works on the fact that n is a prime if and only n divides n choose k for every k lying between 1 and n minus 1. So this is very simple fact that the n has to divide the binomial coefficient n choose k when for any k lying between 1 and n minus 1. So then n becomes prime. So this is how this is the basic idea towards the AKS algorithm. Now I want to define the pth cyclotomic polynomial. So for any prime p, phi of p, which is the pth cyclotomic polynomial, is x power p minus 1 by x minus 1, which is this polynomial of degree p minus 1. So let zeta of p be the root. So 0 of this polynomial, and if you know some bit of ring theory or field theory, then the if you look at this zeta p, so this is a ring generated over zeta p by zeta p over g. So this is a ring. So basically, it's a numbers of the form polynomials in GP with integer coefficients. And for any integer n, you write zeta p over n with the residue ring GP modulo ideal. So basically, this ring means it's a set of polynomials in GP. You consider polynomials modulo n. So residue ring G zeta p modulo the ideal n. And when n is not equal to 0, it's actually a finite ring. So the basis of AKS algorithm is the following. Let n be a positive integer and r be a prime number. Suppose n is not divisible by any of the primes r. Yeah, any of the primes less than or equal to r. So there's a mistake here. So let's start. So you're given n. So you choose the number r which is prime, and first see that n is not divisible by any of the primes less than or equal to r. Now you look at order of n modulo r. So suppose the order of n modulo r is at least log n by log 2 per log n by log 2 square. And for every j between 0 and r, so you look at zeta r. Zeta r, remember, is the root of this rth cyclotomic polynomial. So zeta r plus n is zeta r plus j in this ring. It's a finite ring. So in that case, n becomes a prime power. So this is the basis of AKS algorithm. So you just use the basic information of the ring theory and the fact that a prime divides n choose k for k between 1 and n minus 1. So let me now write down this a case algorithm. Let's start with the odd integer. The first check if n is a power of integer. So one can easily check if a number is a power of integer or not. That's very easy algorithm. First, make sure that n is not a power of integer. Now, by successively trying r equal to 2, 3, and so on, determine the smallest prime r, not dividing n or any of the number n power I minus 1 for I running between 1 and log n by log 2 square. Now, once you have found some r, for a number j between 0 and r minus 1, check if zeta r plus the root plus j power n is zeta r and j in this ring gzp mod n. If the number n doesn't pass the above test, then it's composite. If it passes all of them, then it's a prime. So basically, if n doesn't pass some of them, then already it stops. It's not a prime. But if it passes all the tests, then it's a composite. It's a prime. So you can just have a look. So this is the case algorithm. Now I'll show you the proof of correctness. So if n is prime, then it passes the test by Fermat's-Little theorem. Conversely, suppose n passed the test, then you check the conditions of the lemma. So by definition of R, n has no prime divisors less than R, and R doesn't divide any of the number ni minus 1. So the order of n modulo R exists this log n by 2 whole square, log 2 whole square. So this satisfies the second condition of the lemma, and since the test is passed successfully, third condition is satisfied. So this tells you that n is a prime power. Since n passed the first test, it's actually prime. So basically the lemma tells you that n is a prime power, and because of Fermat's, because of this first test, n has to be prime. So because R, any prime less than or equal to R doesn't divide n. So this is the only non-primality testing algorithm which is deterministic, and is well known as the Agrawal-Kyle-Saxena algorithm, AKS algorithm. Now let's talk about time complexity. This algorithm is a polynomial time algorithm. Its running time is log 5 or log n to the power 5. So R, so the way R we find, so we can find R in log n power 5 steps. Because of that, algorithm requires log 12 plus epsilon n arithmetic operation. So it's not good in practice. Now Hendrik Lenstra and Carl Pomerantz further reduce the size of R from log power 5 to log square. So the time complexity finally is now log power 5. Still, this is not that fast. Now Bernstein again reduced the time complexity to log cube n at the cost of making it randomized. So that way, it's still, I mean, one can make it a bit faster, but it's still not that polynomial time. So this is all I have for the prime and primality testing algorithms. Now I want to, in the last few minutes, I just want to talk a little bit about the factoring. So in RSA algorithm, so you also need to factor, I mean, you need a number, you need to know that the numbers cannot be factored easily, or you need to factor large numbers. So can you factor a number as product of primes? So let's start with a simple example. If you're given the number, if you're given 77, it's easy to see that 77 is a prime. You can factor 77 is 7 to 11. If you're given 11639, still you can factor. I mean, the number is a little bit big, but still you can factor 103 into 113. So now if I give you this number, so can you factor it easily? So by the way, this is so-called RSA 240. So this is a 240 digit number, which is a product of two primes. So it's one of the challenge problems of RSA factoring challenge problems. So you have to factor this number. So this is not that easy. So only recently it was factored. So I'll tell you the story about RSA factoring challenge. So RSA Laboratories, which design protocols for RSA crypto system, has a set of numbers which is a product of two large primes. Then, I mean, if you type in Google RSA factoring challenge, then you can actually see more details about it. So earlier, you see now the RSA companies taken by AMC Corporation, so still they run this RSA factoring challenge. So in this, they give a list of numbers which they generate through some algorithm and ask you to factor. So in December 2019, a research team led by Emmanuel Thom had friends in RIA. So basically, so their group, they factored this RSA 240, and other members of team include Fabrice Boudou, Patrick Gaudry, Aurore Golubic, Nadia Henninger, and Paul Zimmerman. So this is the number. This is 795-bit number, 240 digit, and these are the factors. So as you can see, I mean, if I just give you this number, so we don't know how much time will it take to factor, right? Because we have only two prime factors. But then now we have enough technology that even though this is big number for factoring, so we can factor. So and as you can see, both these primes are almost of the same size. Okay, so this is the RSA factoring challenge. So now I will tell you a bit about how did they factor. So to factor this RSA 240, they spent CPU time, which is around 900 core years. If you really work on a 2.1 gigahertz Intel Gold 613 CPU, these are the specifics of a computer. If you have any computer with these specifics, then it will take 900 core years. Then so this trigger, so they use so-called number field shift Kado NFS method, and this involved different steps. So there's a sieving step. Sieving step took actually most of the time, so 800 physical core years, and RSA matrix step took 100 physical core years. In fact, they did it together with another discrete logarithmic record, and total computation time was roughly 4,000 core years. I mean, basically, discrete logarithm took a lot more time. And they work with the open source software called Kado NFS, which is used to implement the number field shift. So if I give you definition of number field shift, actually I need to introduce a lot more algebraic number theory, so I'll not give it here. And in fact, Kado NFS comprised of 3 lakh lines of code written in C and C++. So they spend this, and so 900 core years, they actually took around less than a year to actually factor this RSA number. So there are other factoring algorithms: elliptic curve factoring method, number field shift, polar row factoring method. So these are the other factoring. So, but still now we don't have any polynomial time factoring algorithm. Factoring is still a hard problem, and that makes RSA crypto system still secure. Now I want to end this lecture with this very simple idea of Fermat's factoring method. And so, and basically every factoring algorithm, they use this, they build up on this Fermat's method. So this is a very simple idea which all of you can understand. Suppose I want to factor 13199. So how do you factor? So it uses a very simple idea that if you can write a number n as a square minus b square, and if a minus b is not 1, then a minus b and a plus b are going to be factors of n. So since a minus b is not 1, a plus b is not n, So you have a factor which is different from 1 and n. So you can factor n. So that's the idea. Let's try to see this. So you want to factor 13199. So you try to find numbers such that n, you can write it as a square minus b square. So you start with a number m which is strictly bigger than square root of 13199 and take the difference m square minus n. So square root of 115 square is bigger than n. So you take 115 square minus n. 126 is not a square. You take 116, 117, and so on. You keep on taking until m square minus n becomes a square. After some time at 132, the number m square minus n becomes a square, which is 132 square minus n is 4225, which is 65 square. Then n is, as you can see, n is 132 square minus 65 square, which you can factor as 132 into 65 and 132 into 60 plus 65. And none of them is 1 and none. So n has the factor 67 and 197. So this is the Fermat's factoring method. So in this, I've tried to give you some ideas about how the probability testing works, how factoring works. So, but still we have a long way to go. We still need to find fast algorithms, new ideas to actually factor or factor a number, or find also check whether a given number is prime or not. And also, okay, so that's all for today. So thank you. Please feel free to ask me if you have any questions.
Thank you, Professor Loishram. Now participants may ask their questions or queries one by one to Professor Loishram.
Yes, sir. Yeah, so I see one question here. Can you explain a little bit of Riemann hypothesis and distribution of primes? Okay, yeah, sure. So I'll share a slide and also you actually, yeah. Okay, let me just give me a moment. Okay, so I'll explain it. Okay. Okay, so yes. Let me share the screen. Can you see the screen?
Yeah.
Yeah. So this is the Riemann zeta function. So for a complex number S, which is, you can write as sigma plus it, where sigma is the real part, t is the imaginary part. With sigma bigger than 1, you define the function zeta of S to be infinite sum 1 over n power s, where n goes from 1 to infinity. It has the Euler product formula given by by fundamental theorem arithmetic, actually you can write zeta of s as 1 over 1 minus 1 over ps, or p is set of all primes. And there's a notion of, if you have learned some complex analysis, then you can, one can easily show that this zeta of s can be analytically continued to the whole of complex plane. So-called resulting function is called Riemann zeta function. We still denote by zeta of s. And zeta of s satisfies this functional equation, which is given by zeta of s is 2 power s times pi power s minus 1, sine of pi s by 2, gamma of 1 minus s, and zeta of 1 minus s. So basically, yeah, if you know zeta of 1 minus s, you know zeta of s, and vice versa. And here gamma is the gamma function defined here. So because of the zeros of gamma function, one can see that Riemann zeta function has zeros at negative even integers. So at -2, -4, -6, zeta function is actually zero. So these are called non-trivial zeros. These are called trivial zeros, and any other zero, these are called non-trivial zero. They lie between this real part. So if something is is a zero, it's a root, then the real part lies between 1 and 0 and 1. So, and the Riemann hypothesis, which is $1 million problem, is the following: if S is a sigma plus it is a non-trivial zero, then real part is half. And in fact, 1 plus it can never be 0. This actually implies prime number theorem, so I won't go into it. But I'll tell you how this, so how this is related to this prime number theorem. So there's a notion of this Chebyshev function, which is, I didn't define it here, but this is a product, sum of log of prime powers which are less than x. So psi of x has this this is equal to x minus x power rho by rho minus log 2 pi, where rho runs over all the zeros of Riemann zeta function. So now, if the zeta function is has only the if the zeros of zeta function lies on line half only, then in fact you will have this Chebyshev function will be like x plus some error term, which will be x power half. So this is how actually the Riemann zeta function is connected to distribution of prime. So there are a few more things to do, but right now I can only tell you this. If you want to ask, if you want to know more, maybe you can write to me or you can talk to me later on. So this is the main fact here. So the Chebyshev function is actually given by this. So this is the information.
Is there any other question? If no further question available, I conclude the last technical session of the webinar. Thank you, Professor Shantaleshram, for your nice and informative lecture. I also thank Professor Leshram for taking time out of his busy schedule. Now we arrive at the end of the webinar. Ms. Devasmita Dotto will give the vote of thanks.
Thank you, Sharmadi. Good afternoon, everyone. On behalf of the Advanced Research Center of Mathematics of Lady Brabourne College and the entire organizing committee, I would like to convey our hearty gratitude to the respected speakers, Professor Abhishek Adhikari Sir of Presidency University and Professor Shanta Laisram Sir of Indian Statistical Institute, New Delhi, for granting their valuable time to enlighten us with their respective subject matters. Their profound and comprehensive vision has indeed enlightened our knowledge and moreover kindled our curiosity in the number theory and cryptography. We express our earnest gratitude to them. I like to express my sincere gratefulness to our principal madam, Professor Shuli Sarkar, for allowing us to organize the webinar and for encouraging our genuine endeavors. I am grateful to our TCS Dr. Porna Ghosh and IQAC coordinator Dr. Indrani Chaudhary Dutt for their positive encouragement. It would be my pleasure to congratulate and thank our head of the department, Dr. Sharbani Mukherjee, for leading our aspiring initiative in the forefront. I am truly fortunate to have my motivated and devoted colleagues and respected professors of our department and other department of the college for their extremely moral support. I express my deep appreciation to Richa Mehrotra for technical support. This webinar would have never been organized without the help of my beloved students. Their 24/7 constant support and encouragement leads the webinar to a successful one. Last but not the least, this webinar would have never been successful excepting the cooperation of wonderful audience. Also, we are happy to announce that we are going to organize a 3 days national level webinar on R programming and ring theory during 6th, 7th, and 8th of September. We appreciate and thank everyone for your valuable presence, and also we are looking forward to your active participation on the upcoming webinar. I hereby announce the conclusion of today's webinar. Thank you very much.
Okay, thank you.
Thank you. Thank you, sir.
Okay, then logging off now. Okay. So have a nice day. Thank you.
Thank you, sir. Thank you very much.
Thank you, sir.